And then I want to show you, let me see. Okay. I just want to show a couple of things here on Canvas. First of all, thank you for those of you that tried the practice problems from, or the first set of practice problems. I did post the key. Those of you that didn't get a chance to do them, I encourage you to practice before looking at the key. It's really, I think these is more than just getting extra credit. It's kind of like preparing you for the exam. So you kind of like bit by bit study and practice. So just give them a thought. And then I opened another one, another set of practice problems for the protein analysis segment. And I have an assignment which will be due by midnight on Sunday. So also once people submit, I will also open the key for you guys to look at. And if any of you like solved it and looked at the key and you're still confused, we can bring it to the class and we can have a discussion. I'm open to that as well.
Okay, quick question. Is that assignment extra credit or
extra credit?
Okay.
These assignments are 5 points extra credit. You won't see them in the grade book. I'll just look at your assignment and I put it on my end on my Excel sheet. And then at the end will be just added to your total points. Okay, so the assignments are open under assignments. You can see here, if I go there, you'll see 2 assignments already. One of them is passed and one is due this Sunday. Okay, the other thing I want to point out on modules is we're going to talk about a lot of methods, and we definitely don't have the time or it's beyond this course capacity to dive into the analytics and the principle of each method. I will be just, glancing over them, giving you an overview and giving you a few applications to kind of like link those analyses to real life applications. But if you want to learn about each of these, the principle of each of the methods that I'll be covering, I have included here related reading materials. So if you go here, I have developed document for each type of analysis that summarizes principle and applications. So you can use that as a resource. Also, I have developed another document here, protein structure characterization. It again talks a little bit more in detail and supplements what I'll be covering in class. So in addition to the chapters, I have up here too. So make sure that if you want to learn anything addition than what I cover in the class, these will be backup information. So this is backup information for you to understand the methods, because I don't have time to go into details in depth. However, I won't be asking in an exam specifics. But if you understand the methods, then you'll be able to give an application. Right? So it's for your own understanding, but I won't be asking specific on principles of detailed principle of methods beyond what I cover in class. All right, so I'm gonna stop sharing that and start sharing my PowerPoint. All right, so we'll go to where we left off last time. Okay, so let's have some, like usual, recap questions to get you back in the zone of where we were. Can you give some examples of protein analysis categories? So under protein, under the umbrella, when we say protein analysis, what do we mean? What does it encompass?
Like characterization?
Protein characterization is one. We're going to talk a lot about protein structure characterization, and then later we'll be talking about functional characterization. So yes, protein analysis covers characterization, covers identification. What else?
Isolation and separation.
Yes. So under protein analysis, also the fact that we need sometimes to isolate the protein to characterize it, and sometimes we isolate it to produce an ingredient. Okay, what else? One last thing that is the easiest of them all.
Labeling.
So quantification for labeling, yeah, for quantification for labeling for other purposes as well. So labeling is an application for quantification, but we do other applications for quantification. Those of you that do a lot of that in the lab, when do we need to quantify proteins? Quantity.
When you're trying to figure out an extraction method and whether it is going to give you the best yield or not.
Yes. So looking at protein quantification when we're isolating and looking at protein purity, was the extraction method sufficient to give us the purity that we were looking for? Or was it also sufficient to extract most of the protein from the starting material? Good. Can you give an application for characterization? An example characterization. We haven't gotten through characterization, but maybe some of you know and have an idea of what we do to characterize and why. The structure.
Denaturation temperature, like DSC.
Yeah, denaturation temperature. So we need to know at what temperature our protein denatures so that we can determine the impact of processing on our protein, for example. Great. And isolation, I talked about that example. We isolate the protein sometimes to characterize it, to determine method of extraction or optimal method of extraction, to produce ingredients. So great. We talked about a lot of methods, but briefly about protein quantification. Can you name one or two? And
Under air classification, that's one of them that did it based on like the density of the material.
That's for separation of the protein, yes.
Yeah.
So air classification is definitely for protein separation, yes. So my next question was on protein quantification method. What protein quantification methods do you remember we covered last time?
Dumas and the Keldal, how do you say?
Yes. Yes, Dumas and Keldal both are based on determination of nitrogen. One is an instrument based on nitrogen combustion, and the other one is chemical based on digestion with acid, and then distillation and titration. We do have a lot of methods we use for research methods, especially when we have purified protein solutions. Some is based on UV measurements, some is based on reaction with a dye like Bradford, some is based on reducing like the bisynchronic acid, which is, we call it for short BCAA. So these research methods, if you want to quantify, usually we need a standard and have a standard curve and try to get an estimate of the protein. All right, great. So on what basis protein separation protocols are developed? So what characteristics of the protein we rely on to separate it, basically?
Based on their biochemical characteristics, for example, solubility, size, charge.
Absolutely. So solubility in different solvents. So solubility at different pHs, solubility at different salt concentrations. We can also, based on the protein characteristics, adsorptive characteristics, we can separate based on size. We're going to talk about size now. So biochemical characteristics, size, charge, solubility in solvents, in water, in different pHs, different salt concentrations. Great. Can you think of chromatographic methods for separation of proteins? We talked about a few last time.
Ion exchange.
ion exchange is very much used, whether in a laboratory research setting or in industry. We talked about Agripor last time. They produce whey protein isolate using anion exchange chromatography on an industrial level. So ion exchange, what else?
HPLC.
Yes, what type of, well, ion exchange can be, okay, so high performance liquid chromatography, and then you have the low pressure liquid chromatography, but that is correct. But what I was thinking about, what type of HPLC or liquid chromatography you would use. So ionic is a type. What other type do you have?
Hydrophobic HPLC.
Yes, hydrophobic interactions, which is mainly based on covering the charge of the protein by high salt concentrations so that they would interact with the hydrophobic resin or media via weak hydrophobic interactions and get separated from those that won't interact via those components that won't interact via hydrophobic interactions, or they can be separated based on their degree of hydrophobicity. Great. So another form is size exclusion, and we're going to talk about that in a bit here. We talked about protein separation examples based on difference in solubility. So pH, solvent, salt. So we talked about that. The grade item we haven't covered yet. So any questions from past lectures? Anything from whatever comes to mind?
This is kind of dumb question, kind of going back to the first lecture. Glycine, did you say it's not chiral?
Yeah, it's not chiral, and it's not dumb question, by the way. I don't believe in dumb questions. So any question is a valid question. So it's not chiral because by definition, a chiral carbon, because the carbon forms 4 bonds, that means that every bond you have a different group. So the glycine have amine group, carboxyl group, and then 2 H's instead of an R group that is made up of like a hydrocarbon group or a ring structure or anything else. So that makes it non-chiral. It's nothing like of major substance for you to know and remember. It was just a comment.
Then when you're titrating a protein solution to the endpoint, and you continue to titrate, does the pH, pH changes slowly after that, or does it change quickly?
Are you talking about the buffering effect?
Yeah, if you're titrating a protein solution to a certain pH with an acid,
Yes.
example, then after you've reached, I think it's the isoelectric point, then would it just
So
not change as
when
quickly?
you, yeah, so what happens when you titrate, depending on the protein and depending on its net charge, it will resist pH change. So usually, for example, so let me give you an application that makes sense. So if you want to prepare a protein beverage, let's say acidic protein beverage, and you want to make a protein claim and you say, I want to put 5% protein in there. If I want to reach a pH of 3.4, let's say, or 3.2, usually beverages are between 3 and 3.6 in the market as acidic beverages. So the more protein you have, let's say if you have 1% protein versus 5% protein, when you're adding an acid to reach a pH of 3.4, the more protein you have, the more acid you need to add to reach to that pH. Then that's a problem actually in industry with sourness of protein beverages because the protein resists the change in pH and you keep adding acid until you get to pH 3.4. So a 1% protein solution versus a 5% protein solution, to reach the same pH, you would need more acid. Does that kind of answer some of what you're asking?
Yeah, I think so. And then the last one, the lysyl group, LYSYL. Is that another name for the R group?
Lysyl group?
Yes, it's in the slides.
Which slide? I'm not remembering. Are you talking about lysine amino acid?
Maybe.
I'm not sure what, yeah. I can't think of anything to answer. Does anybody know what Paul might be thinking?
I think when I've seen that in publications, it's referring to lysine.
Lysyl group?
Yeah.
Lysyl group? Okay, yeah. Okay, so it's
Okay.
just, yeah. Good, thank you. Any other questions?
I have one, Pam, from last lecture. You mentioned in last lecture that when you dry a protein at its isoelectric point, that it's irreversibly denatured. Why is that?
So I was going to talk about denaturation after today's lecture, after protein analysis. You don't want to leave a protein under a condition that disrupts the natural structure for a long period of time. Then let's say if you put the protein under acidic condition for a long period of time and very high acidic condition or very high alkaline condition for a long period of time, even if you return it back to neutral, the denaturation, the protein will unfold and then refold forming different types of bonding, not the same as the original. And these bonding can be within itself or with other proteins. So when you have proteins at the isoelectric point left as is, even at low moisture of 5 to 10%, then you're going to start having irreversible protein-protein interactions because there's no repulsion, even at the low moisture content. And if you want to just put them back in solution, they're already formed no longer reversible interactions. Does that answer your question, Laura?
Yeah, I didn't know if there was something like specific to that, but it makes sense like as to why when we bring protein solutions up to like really high pH, that then it's easy to bring it down quickly because it's in solution. But if you dry it and then store it, it's in the freezer and that like, and it's not natural formation for a long time. So that makes sense. It just seems, I didn't know that it would like completely mess it up, completely denature it for the future. So
yeah, it would. I mean, the longer it is, and also depending on moisture content. So later in the next lecture, I'll talk about impact of moisture content on denaturation and pH on denaturation. So we will explore that a little bit more and maybe help with your question a little bit more. Good, great. Any other questions?
So I just had a quick question on like freezing and how that affects, because I know in secondary structure, we talked about how it's driven a lot by hydrophobicity and sometimes water can get expelled.
Yes.
Does that mean freezing can denature proteins to a certain extent?
Depending on the moisture content. So if you have moisture content beyond the above the monolayer, and I'll also talk about monolayer later, although that's not my favorite topic, it's Ted's favorite topic. But if you have a little bit of a moisture content above the monolayer, so the water actually, when it freezes, it forms crystals. And of course, the crystals take volume more than liquid water. So when you thaw, so the crystals will, dissolve, but then they cause kind of some structural change because they change from liquid to ice and then back to liquid. And every time you repeat the freeze thaw, you are disrupting the protein structure. So gradually you're causing denaturation of the protein. Although the denaturation at freezer temperature is much slower, but the presence of water and how much you have water there impacts denaturation over time.
Okay.
Okay, great, thoughtful questions. What else?
Hi, I have a question.
Yes, hi, Sam.
So consider, for example, I have the same protein and I dry it. So let's consider the scenario that I have it on the isoelectric point and I dry it on the spray drying and I dry it on the freeze dryer. would I have the same amount of ratio of denaturation considering both, or will spray dry will be more because of the heat? Like
I would assume theoretically with spray drying because of the heat involved. So we've done work to compare impact of protein, impact of the drying condition on the protein structure. And we found that the protein we produce in the pilot plant are slightly more denatured than the protein we produce in the lab because due to freeze drying. So definitely the presence of heat kind of impact how much the unfolding of the protein, and especially if you have like high salt content or pH close to the isoelectric point, the rate of denaturation becomes higher. And again, next lecture, I'll show figures to show the relationship of salt content and denaturation temperature, water content and denaturation temperature, and also pH and temperature effect on later on when we talk about solubility, for example, we'll have all of that kind of examples, the relationship at certain pHs and certain salt concentration and how it impacts denaturation in the presence of heat. Good. Yes. That's great. What else? Anything else? All right. So every year I teach this lecture, this protein analysis, I add examples from research we do in the lab, and the lecture goes longer and longer, but I feel like these examples are really nice examples to link the theory to an application. So this might be a little longer than 2019 when I taught this because I have more examples to share. And I tell the students, if I don't cover all content that I wanted to cover in the semester, that's fine, as long as I give enough material and relevant examples, that's fine. So, all right, so last time we talked about separation of the protein using pH and salt and different adsorption characteristics. Now I'm going to talk about separation or purification of the protein based on size. So the one simple thing that we do, and we do often, is not necessarily to separate proteins from each other, but mostly if we use salt to isolate the protein or precipitate the protein, or we use a lot of acid base, we put the protein at alkaline, then we drop the pH to acidic, then we neutralize, we are producing NaCl in this process, NaOH, HCl, up and down, we're producing salt. So at the end of the day, you want to remove salts. And sometimes you also want to remove small sugars. So you can purify your protein even more. So dialysis is a very common technique we use mostly to remove salt. And sometimes we do it to remove small sugars as well. But it kind of is an essential step at the end of protein isolation using alkaline or salt extraction, because you want to remove the salt that might impact structure and functionality. So you don't want to have high salt concentration, because first of all, high ash, high sodium is not desired in an end product from a nutritional perspective. Also, it impacts how the protein is going to be soluble, is going to gel. Sometimes a little bit of salt helps, but too much salt is not desired. So dialysis is basically you take a tube of a membrane, I usually bring show and share to the class so you can visually see the tube. But the tube is very thin material and it has pores. And you can purchase tubes with different pore sizes. So you can get tubes with 500 daltons. That means 0.5 kilodalton, very small. And you can get 1 kilodalton, 3 kilodalton, 10 kilodalton. So you can really choose the size of the pores based on what molecules you want to get rid of. And yes,
I have the dialysis tubing in my hand if you want to.
Oh, I'll stop sharing.
I don't
so
know
that
how
you-
well you can see right now, but because of my lighting, but this is the tube that it comes in, and it's just like pulled out a little bit more here. I don't know how well you can see. I don't have the best
Yeah,
camera.
and when you pull it, you just pull a certain length based on how many milliliters of samples you have. And usually it comes with instructions, how many milliliters per how many centimeters of the tube. And then the tube is open, so you cut it so it's open from both sides. You close it. Do you have the clamp?
I can get it.
Oh, that's fine.
Okay.
So it shows in the picture, the clamp. So let's go back here. So yeah, so you clamp it closed, and then you pour in your solution, protein solution with the salt, and then you have another clamp, and you close it shut. And then you put it usually in water. You can do buffer too if you want to control certain pH, but usually it's water. And what happened, diffusion from high concentration area to low concentration area. So the salt start moving out to the bucket where you have your dialysis tube, and you reach equilibrium. And when you reach equilibrium after 3-4 hours, you throw out the water and put fresh water. And then after a few hours, you reach another equilibrium. So you continue doing washes. The more salt you have and the more protein solution you have, the more washes you want to do, so that at the end you reach an equilibrium where you have very, very tiny amount of salt remaining. You will never get to 0% salt because it is an equilibrium process. But the washes helps reduce the amount of salt to as much as you can go. Sometimes salt interact very strongly with the protein. No matter how many washes you do, you still have some amount of salt left in your sample. Another thing, that some tubes come with polyethylene glycol layer, so that instead of, so to prevent water going into the tube, basically, so that you don't have bulging, because water will start going from a diluted place to a concentrated place. So you really want just to get the salt from a concentrated place to a diluted place. So you prevent a lot of bulging of the tube if you have tubes that are that have a layer of polyethylene glycol. So the kind of like resistant to water migration. So it is a very common step we do after purification, just to remove salt, and sometimes small sugars as well we can get rid of. And the most common molecular weight cutoff we use is 3 kilodalton. 1 kilodalton is more expensive than 3 kilodalton. And with 3 kilodalton, you don't risk losing proteins. 10 kilodalton, you might lose small molecular weight protein, so we don't recommend that. So the protein remains concentrated in the tube, and after that, you take the tube and you either want to subject it to drying or any analysis that you have in mind, but at least you get rid of the salt.
I have a question, sorry.
Yes. Yeah,
I'll ask a lot
that's
of
good.
questions.
No, keep asking.
Usually, I was reading some procedures, and for dialysis, usually carried out at cool temperature, right?
Yes.
Yeah, like for example, if we increase a little bit the temperature at the point and not denaturate the protein, wouldn't be more effective, the removal of salt?
But it would be effective in microbial growth as well.
Oh, okay. So that's why you keep low.
Yeah, so usually dialysis is done over a day or two, and you don't want any mold or yeast growth. So we do that in under cool conditions. Definitely with higher temperature, you have better kinetics, thermodynamics, but we don't want to do that because you don't want any growth. Good question. All right. Okay, so separation by size we can do also, other than dialysis, which is also a membrane separation, we can do membrane separation in different ways. So we have a very, very small scale here. You can see if, let's say you want to separate flavor compounds from that are not reacted with proteins from proteins. You can use, I say flavor compounds because it's just recent that Gary wanted to do that. So you see these tubes, and if you have a very small amount of sample and you really want to remove certain compounds and separate them from the protein, you get tubes with membranes, also with a specific cutoff. You can also have different cutoffs. 500 daltons, 1 kilodalton, 3 kilodalton, 10, even 50 kilodalton. So you can get different sizes. And sometimes you separate proteins from peptides. Sometimes if you do a hydrolysis and you really want to get rid of the proteins that did not hydrolyze, you can separate and take the peptides and fractionate them and study them further. So you can do that on a very small scale, or we can do it on a little bit larger scale. And we have something similar in the lab where we use this especially when we separate using salt. So we apply a little bit of pressure and we use membranes, and then your solution goes through, and with a little bit of pressure, you have a pump that pumps the liquid in, and then you get permeates, which are lower than the cutoff of the membrane, 3.5, let's say, or 3,000 kilodalton, 3,000 dalton. So the permeates go through, and then you concentrate and retain the retentate, which basically you wash several times, and then you get the solution that didn't pass through the membrane, and that would be your retentate. And we do that a lot to purify the proteins more, not just from salt, from any soluble sugars or colors, or even soluble, any compounds, for example, that are soluble in water and you don't really want them in your proteins. You can do this on the larger scale, obviously, in industry. So in industry, there is membrane filtration, and it's a huge industry. So you can produce whey protein isolate by membrane filtration, where I'll show you example later on about production of whey protein isolate with membrane. But you can have large size membranes, and also you can have different membranes, either microfiltration or ultrafiltration, nanofiltration, or reverse osmosis. So that is based on the size of the pores. And I'll show you examples where different sizes are used. And oftentimes you separate small molecular weights or smaller molecular weight from larger molecular weight, and also concentrate. So here's an example. Let's say if we look at milk system. So in milk, what do we have? Let's look here. We have ions, we have lactose, small molecular weights, we have proteins, colloidal phosphates, caseins, whey, vitamins, we have fat globules, yeast, mold, bacteria. So each of these components have different sizes. So here you have the particle size versus the molecular weight. And then here's the characteristic, either ionic, molecular, macromolecular, cellular, macro, or microparticle. So we can do ultrafiltration. We can do reverse osmosis will get rid of ions. And nanofiltration, more like salt and lactose. And ultrafiltration also get rid of salts and lactose and retain the proteins. Microfiltration, proteins can pass through, but fat globules won't pass through, and bacteria cells won't pass through. So to see it more visually, let's say this is the milk system. You have the bacteria, the fat, the protein, lactose, minerals, water. Macrofiltration, you retain bacteria and fat, and everything else will pass through: protein, lactose, minerals, water. Then you want to isolate the protein, you use ultrafiltration. So protein is retained, lactose, minerals, water pass through. You want to collect lactose to produce a lactose product. You use nanofiltration, lactose is retained, minerals goes through, water goes through. You want to purify the water from salt, you use reverse osmosis, and you purify your water. So pretty neat system. Here's a diagram that shows an actual application for production of whey protein concentrate and isolate. So here you have the cheese fat where you produce the curd, then you separate the curd from the whey. You get the whey, and if you subject it to ultrafiltration, what you get is all the proteins, everything proteins and bigger, you get here in the retentate. Everything lower than the protein size, salts and lactose, they go here, and the byproduct is whey permeate. You can produce lactose from that permeate. But if we continue here, the retentate is a product that is called whey protein concentrate. And depending how much you run through and purify, how many times you wash and how many times you purify, you can get a concentrate up to 80% protein. But you can also get as low as 34% protein. So it depends on the number of washes and passes and also the size of the ultrafiltration membrane pores. Now you have WPC. Let's say I want to produce WPI, which is an isolate with over 90% protein. I do macrofiltration here. So the isolate, the protein is going to go through. But here, anything that was retained in the ultrafiltration that is bigger than the protein, the fat globules or aggregated proteins, large molecular weight proteins that are aggregated, will be in the retentate. And lipids like phospholipids will also be in the retentate. And then your permeate would be your proteins. Then you get a whey protein isolate here. And then the retentate is another byproduct. We call it whey phospholipid concentrate, or if some of you might know it as procream, if you have heard of that term before. Any questions here?
I had what happens to glycoproteins, like proteins that have lactose molecules on them when you do ultrafiltration? Are they mostly retentate?
So the way you get glycoproteins with lactose, there must have been some heat treatment that might have resulted in Maillard reaction, right? So you won't naturally, beta-lactoglobulin and alpha-lactalbumin are not naturally glycosylated or glycated. So when you have some heat treatment that caused lactose to react with whey protein, then you're basically, depending on how much, again, you have reaction, the molecular weight will change. But anyway, they will end up here in the retentate with the protein if they are chemically bound to it. And depending on the size that we end up getting, if it's advanced Maillard reaction and you have a lot of glycation, and sometimes you get protein polymerization due to Maillard reaction, then we will lose them here with this this byproduct, the phospholipid concentrate. So phospholipid concentrate or procream does also have whey protein. So it's never 100% separation of proteins from other components. So you do have, even in the byproducts, you do have some proteins in there.
I have a question for the processing. When we reach to whey protein isolate, I know there are other products called whey protein hydrolyzed.
Hydrolysate, yeah.
Is it like we continue, or like is another processing?
Yes, it's another processing. So oftentimes the hydrolysate are produced from isolates. So if you want to produce a hydrolysate, then you take the protein isolate and you subject it to either batch hydrolysis or membrane or continuous hydrolysis where the enzyme is immobilized on the membrane. And then the protein solutions go through, get hydrolyzed by the enzyme, hydrolysate pass through the membrane, through the pores, and then you can continue using you wash and you continue using that membrane with the embedded enzyme. So that's an additional process to produce a hydrolysate. Good, that's great. Anything else?
I have a question about the maintenance of membrane processes. Like how often do you have to like replace the filters?
Oh yeah, so membrane fouling is a big deal where the protein can just build up on the membrane and also block the pores. And there should be like continuous washing depending on the consistency of the solution or what you have. Some component might cause more fouling than others, but there are definitely certain washes that you have to do to make sure that the membrane is clean and you have most efficient filtration. Laura, what was the cleaning that you used in the pilot plant?
I know we used we used some water and heat, but we also used caustic solution. So they would just get it in like big containers, and it was just called like caustic. I think we also used acid as well.
Yeah, so basically alkaline washes would help solubilize the protein and get it out, basically. Yeah, good.
I have
So,
a question.
yes.
I know that this dialysis, you have to change the buckets every couple of hours, and so that can lead to having to come in at like the middle of the night. What would there be negative repercussions to skipping that middle of the night one?
So, I mean, you can, it's mostly the number of washes which is important, the number of time you change. What I usually tell my students, if you want to start dialysis, start it really early in the morning, and then make sure you have at least 3-4 times washes every 3-4 hours before you go home. Maybe you want to come back at 8 or 9 to one wash, but then you can leave it overnight and then wash, and then have a couple of washes in the morning again. So it's okay to leave it overnight. You will reach equilibrium and it won't help. The longer you leave it doesn't mean you're removing more salt. It's just it reaches equilibrium, but for the sake of not having you come at 3 a.m. in the morning, I say leave it overnight and then come change it a couple of times the following day.
So why is there a maximum of 12 hours that it can be left in dialysis?
I mean, again, we want to make sure there's not a maximum of 12 hours. It's just you don't want to leave it long time so that molds and bacteria grow. And I think it's kind of like one student passing it on to the other. They would say, oh, overnight means 12 hours. But usually you don't want to leave your dialysis more than 2 days. I mean, 3 days is a stretch. So you start in the morning and then the next day, sometime midday, you end the dialysis, freeze dry your samples. That's kind of the ideal situation.
Considering whey concentrated isolates, I remember I was watching the previous videos you mentioned, usually isolates will have a taste that's not so pleasant, right? Comparing with concentrates. But when, no, not necessarily. Due to exposure usually, of some groups, no?
Taste? No, I don't remember saying that.
Oh, usually, maybe I thought I heard.
Well, usually when you isolate, the more you isolate the protein, the more you take stuff out. And that might cause like flavors, that might potentially cause off flavors. But the protein, if it's denatured or if it's hydrolyzed, and if you have a lot of hydrophobicity, then it will impact the taste. Yes. So anything that might change the protein itself, especially hydrolysis, might impact the taste. In terms of flavor, it really depends on the odors, that mean the volatiles. It really depends on the crop or the original source of the protein. And sometimes flavors just like to interact with the protein and just get carried with it and get concentrated with the proteins getting concentrated. I think maybe I said that.
So in theory, when you hydrolyze a protein, won't necessarily change the taste of it, like flavor.
When you hydrolyze the protein, yes, you can change the taste depending on the degree of hydrolysis. So if you have a high degree of hydrolysis, you tend to get sourness and bitterness. If you have limited degree of hydrolysis, and depending on the enzyme you use, If the enzyme generates a lot of hydrophobic peptides, then you, even at low degree of hydrolysis, you still get the bitter note. But if there's an enzyme that generates more hydrophilic type of peptides, then the bitter note is less. But yeah, anything you do will have repercussions, so we just have to be careful. Okay. All right, so size exclusion is another form of chromatographic separation, but it's based on size. And we use that quite a bit for analytical purposes and sometimes semi-quantitative, semi-preparative. So when we want to isolate certain fractions of proteins and study them more, or when we want to study the ratios of different protein components based on their size. And in size exclusion, very briefly, you're separating based on size with the large molecular weights, with the large molecular weight coming out sooner than the small molecular weight. Why? Because your column and your media is made up of particles that have different pore sizes. And you can purchase columns or media with different pore size range. You can separate different ranges of protein molecular weights. So you just have to know what your molecular weights are and then talk to a technician and then purchase the right column with the right range. But basically, proteins that are small in size have access to almost all of the pore sizes. So they would go into the pores of the particles and get delayed. And those that are large will not go into the pore sizes and they would just go with your void volume. So you have the very large molecules don't go in anything and comes out with your void volume. And those that are the smallest will come out with the entire internal and complete volume of the column. And then those in between will come out in between. And usually we run, if you want to determine molecular weight, we run standards of different molecular weights and we plot the standards to kind of determine try to estimate the molecular weight of your samples. Let's think about this for a little bit. Sometimes you have a mixture of protein and you just want to isolate and purify a certain protein for further analysis, whether it's an enzyme or an enzyme inhibitor or a specific protein, you want it to be very pure. Sometimes you do sequential separation. Sometimes it has to be at least 3 different modes of separations to get a decent isolation. So here's an example where you have a protein X with a molecular weight of 90 kilodalton and a net charge HPH7 of +5. And you want to separate it from a protein Y with molecular weight of 30 kilodalton, but the same net charge at the same pH. And another protein with very close molecular weight, 89 kilodalton, but lower net charge. Which of these approaches would you follow to get to that one protein isolated from the other two? Let's see, we have people in the chat. Laura says A. All right. What else? Who else will be? Radhika said G. Any other? C. Okay. What else? D. I'm seeing all the letters of the alphabet. F. Nobody's going to say H? Okay. So the correct answer is G. So why is it G? It doesn't really matter the order. So if you want to do two-dimensional separation, in this case, I gave you 2 characteristics. One is based on size and one is based on charge. So I want to do 2-dimensional separation. So cation exchange, that means it's ionic exchange, but it's exchanging positive charges, molecules with positive charges. We can separate the proteins that have +5 from the protein that has +2. So these two will be coeluting together, but I want to separate them further. They're different in size, so I can use size exclusion. So A is correct. You can do precipitation using ammonium sulfate salt. If I know a little bit about my protein, I know what concentration might precipitate protein Z. Then I precipitate C at a particular salt solution concentration, and then I have these two. Then I can use a molecular weight cutoff, ultrafiltration, where I can say, okay, I'm going to choose a 40 kilodalton cutoff. So my 30 kilodalton can be separated from my 90 kilodalton. Yes, so that can work too. Or C, it doesn't matter the order. You can do size exclusion first, then cation, or cation first, then size exclusion. Order doesn't matter as long as you do the necessary dimension of separation based on the given in the question. So all of that. Okay. This is the most annoying thing I've done as a postdoc. Is separation of a particular enzyme inhibitor in milk. And this enzyme inhibitor is associated with the casein. So you start with milk and you want to isolate this inhibitor and do enzyme kinetics on it. So you want it in the purest form possible. So it's a very, very tedious isolation procedure, but it kind of gives you an example of everything we talked about. So first, or some of the things we talked about. So first you have the milk, so you want to remove the fat. So you do the defatting step by centrifugation, you take the fat out, and then you have the defatted milk. Then if you ultracentrifuge, you precipitate the casein from whey, and then the casein has that inhibitor associated with it. So you throw away the whey and take the casein.
Yeah, he's on the chat. Oh, yeah, he just got emailed today, or she.
Holly, you're not on mute.
I'm so sorry.
That's okay. All right, I thought you were talking to me for a second. All right, so, and then in that casein, you acidify, and what happens is you get an acid precipitate, you throw it away, and then take your supernatant, and then you do salting out. And then you throw away the supernatant and take the precipitate. You dialyze to remove the salt, and you make it up into a solution, and again use certain you add salting out again, you salt out at a different concentration of ammonium sulfate. Then you throw out the precipitate, you get the supernatant, you dialyze, and you have your inhibitor in this supernatant. So how did we come up with this entire procedure? It was just, first of all, you need to understand the characteristics of the different proteins you have in the system, which will be separated by ultracentrifugation, which will be separated by acidification, which would be separated by a certain concentration of ammonium sulfate. So it doesn't come by just trying first time and you go lucky. No, it takes a lot of trials and also characterizing and testing purity and then finalizing a procedure. But luckily I wasn't the one to kind of come up with this procedure. It was already optimized and I just followed it, but it was a very tedious procedure. Okay, so I will give you a 5 minutes break before we start talking about structural characterization. Let's say we come back at 3:55. All right, let's come back. I think we gave you 2 extra minutes. Okay, I just got distracted myself. All right. All right, we have almost everybody back. Let me share my screen again. Okay, now I don't remember if in your copy of the slides you have those boxes filled or not, but do you want to name a few if you don't have the boxes filled? If you have the boxes filled, don't bother. I don't remember. Do we have the boxes filled for your copy? Yeah, I see.
No.
The boxes are not filled in
Boxes are
your
not
copy.
filled.
Okay, good. Okay, great. So now we're going to move into structural characterization and identification. And I will tell you as we go why structural characterization of the protein is important. I'll give you lots of examples. And so that's an exciting bit of, I mean, I don't know if this is my favorite topic. I have lots of favorite topics, but this is really kind of the heart of everything we do is understanding protein structure and identifying proteins. Can you name some characterization, some structural characterization you can think of for proteins?
Surface hydrophobicity.
Okay, surface properties. From the surface properties, it could be the hydrophobicity of the protein on the surface. It could be the charge on the surface. It could be the amount of sulfhydryl groups exposed, because sulfhydryl groups can potentially lead to polymerization. And if they are exposed on the surface, then that means you have high tendency for polymerization. So surface properties, perfect. What else?
Amino acid composition.
Amino acid composition, of course. So when we look at protein functionality, we think about physical functionality and we think about biological functionality. So amino acid composition leads to understanding potentially essential amino acids present, nutritional value. Good. What else?
Temperature of denaturation.
All right. So structural modification, changes in the structure. It could be tertiary structure denaturation. It could be secondary structure. It could be quaternary structure. So denaturation, yes, good. What else?
In our lab, we measure ratio of alpha helix to beta sheets using FTIR, but I don't know the one name.
Yeah, so that's, yes. So that is structural characterization in terms of
You have
what?
Your voice is a robot.
All right. Oh, that's really bad.